Welcome, everybody. Thank you for joining us on this segment of Evidence and Reasons for the Christian Faith. Thank you for coming to this channel. This channel is dedicated to exploring evidence and reasons for the Christian faith. This segment will actually focus a little bit on topics related to evolutionary theory. And there were, Peter is very kind to raise some questions about population genetics, and I hope to answer some of them. So, Peter, how can I be of your service today? Is it okay if I read some of your questions to?
Yes, okay, you may go straight by these questions.
Okay, so there was a question on a slide. It says, hey, Sal, thanks for your debates. They were really nice and informative. And Peter says, I'm new to population genetics, so could you explain this formula and what the variables stand for to help us understand Sanford's paper? And let me see if I can open the image and then share it with the with our viewers. And I recognize what it is immediately. It is, let me just briefly share it on my screen. It was from the Journal of Mathematical Biology, and this was a part of the proof for the fundamental theorem of natural selection. That's Fisher's fundamental theorem of natural selection, amended to account for mutations. And that was published in a secular journal in November 7, 2017. I am informed that that set the record for the number of downloads for any article in the journal's history. It was written by creationist, co-authored by creationist John Sanford. Bill Basener is affiliated with the intelligent design movement. He's not, to my knowledge, publicly stated his views about creationism. So that Peter was asking questions to try to understand this. It might be, I would presume, even if Peter probably knows some of the math already, I'm going to walk through some of it kind of for the sake of the listeners who are not totally acquainted with population genetics, but have some math background. Would that be okay with you?
Okay. My questions was for what P and M variable stands for, but you can explain a few points.
Okay, so yeah, thanks for your forbearance. This could be very laborious for those who are not into the math, but I think it's important to try to go through some of the math and to try to understand the symbols. And so if I kind of fumble through this, this is kind of off the cuff, so to speak, we're on the fly. And so this should get kind of interesting. Let me see if I can. I had a debate a couple days ago with Dapper Dino, and I probably had a PDF. Yes. So maybe to back up a little bit, it's easier to understand the symbols. The topic was John Sanford and Bill Basener and John Sanford's paper on Fisher's fundamental theorem of natural selection. I'd worked with both of them on some related things related to population genetics, and so I developed a paper that was talking about fitness, and that was in my debate with Dapper Dino. But in the process, I had a paper that I published through the Blyth Institute. It's an ID-friendly journal, the Blyth Communications. It's not a mainstream journal. They have mostly a secular bent, but they're ID-friendly. And so the way I introduced the problem, what I viewed as problems with fitness, was to actually talk about Fisher's fundamental theorem of natural selection. So just a little bit of historical background. Fisher's fundamental theorem of natural selection. And if you'll forgive me, I'm going to go ahead and just share my screen and just read from the paper a little bit, because I took a lot of time to carefully word it. And reading from this, even though I wrote it, it's going to be a little easier because I tend to fumble with my words. Fisher's fundamental theorem of natural selection was called biology's central theorem, and I'll abbreviate it FTNS. It might possibly have been accorded this status for decades because Fisher himself declared his own theorem to be fundamental to biology. The idea that Fisher's theorem is biology's central theorem is by and large a myth promoted by popular science writers like Richard Dawkins. Joseph Felsenstein, when delivering the 2018 Fisher Memorial Lecture, declared that FTNS was, alas, not so fundamental. So I've pointed out to others that this is kind of interesting that Richard Dawkins is promoting this as biology's central theorem. Most biologists that I know don't really understand Fisher's theorem, and they've never used it in any capacity as a fundamental concept in biology. So this is by and large a myth. And finally, in 2018, probably one of the world's top population geneticists, Joseph Felsenstein, at Fisher's Memorial Lecture, said his fundamental theorem is not so fundamental. So that's a little background on the theorem that we're talking about. Understandably, creationists, the first being Walter Riemann, wanted to attack this theorem because it was claiming to be fundamental. And he sort of suspected that he felt the theorem was used not as a foundation for any population genetics or evolutionary biology, except to be promoted as a myth that evolutionary biology is rigorous. And it is a beautiful theorem mathematically. It's very hard to describe it, how it's relevant physically. Oh, Peter, by the way, feel free to interrupt me. I take no offense. So
no, it's fine. Just say what you know. Okay, yes.
So I'm just gonna. Oh, please go on. Since I know you're in a distant country, I'm gonna have to wait about 2 seconds after I speak because there's a delay. So please go on. I'm sorry.
So now it would be nice that you explain the content a little bit and what formula stands for.
Okay. So how is fitness defined in evolutionary biology? If I may not, I mean, to be very much more specific, let me say not just evolutionary biology, but specifically, not generally evolutionary biology, but specifically population genetics. And I just for the record, the derivations and the concepts I got from Joe Felsenstein's book. It can be downloaded for free from his website at University of Washington. He's retired. This is very generous of him to make his graduate level textbook, Theoretical Evolutionary Genetics, available to the general public. It's the book that the first edition was written in the 1970s, and he's been updating it ever since. They're like 8 or so editions, maybe more. I lost count. So it keeps getting improved over the years. So just in case anyone was wondering, for reference, this is where I got a lot of my definitions. What I did, if one reads Dr. Felsenstein's book, it doesn't use exactly the notation that someone coming from a math or physics background may use. And so what I've tried to do in this paper here, it's published by the Blyth Institute. It's the Blyth Communications. I don't see that they have, do they? Yeah. This paper that I wrote is in the Communications of the Blyth Institute. You can go to their website by the same name and download this paper. It's open access. So what I did in this paper is just to try to relate the notations and conventions in math and physics to those in population genetics. And that's all I did. I did not try to put forward anything brand new. I basically stated what was obvious. What I covered in my paper is what they call the discrete generation version of Fisher's theorem. Dr. Felsenstein will say, well, it's really just Fisher-like, and others will call it actually Fisher's discrete version. Whatever one calls it, it is a good way of conceptualizing what Fisher's theorem is. So the convention in population genetics is what we call absolute fitness. It is basically a growth rate, and I related it to exponential functions, but we don't need to go there. We could just say that if we have, let me see, it's a growth rate. So the absolute fitness, and just for simplicity, Alan Orr pointed out in his in a paper I referenced in this paper that there are actually a staggering number of definitions of fitness. So the definition here that I'm putting in this example is for the single locus haploid model. It gets a little bit more, it needs to be amended to account for other situations. So this is the model that Dr. Felsenstein starts out with a lot, just because.
May I ask?
Sure.
What is single locus, please?
Oh, thank you. They use the word locus to mean gene. And the problem is that's a little bit of a leftover, because now we actually consider things like the effect on a single nucleotide. So that's a very good question. So that's probably a historical leftover. They often use the word locus instead of gene. There are probably some subtle differences between, they're by and large the same thing, but there may be some formal differences. I'm not aware of it. So actually, this is what Felsenstein himself said. He used it here. Let me see. There was a quote by I quoted.
So may I ask again?
Yes, please.
It means so per nucleotide then? Must I read like that? If it's single locus. Yeah?
Historically, it meant the entire gene, but our understanding now of traits could be even down to single nucleotides. And I think that's an important question to try to answer. And I would refer to professional population geneticists on the importance, because the math is the math. And so parts of this, it's like, well, it may not, when we start talking about some of the symbols, the math just kind of independent of what it maps to physically, it doesn't affect the math. So I'm sorry if I can't answer that more comprehensively, and I think it's a good question. So there was a quote by Dr. Felsenstein, and I saw it here. Right. So Joe Felsenstein said, Fisher's and Wright's one locus equations turn out to be approximations, sometimes bad ones. Why don't I just read the whole quote? Fisher's and Wright's one locus equations turn out to be approximations, sometimes bad ones. The mathematical tools at hand have not revolutionized our understanding of the evolutionary process. Many evolutionists will fail to find the clear and simple messages that population genetics theory once seemed to promise. And that was from Felsenstein's paper, Mathematics. Let's see. Mathematics versus evolution. So I may have misreferenced it. So the term, they will use locus, and I think it's a good question how extensible this is to individual nucleotides. I've seen it being tried to apply to nucleotides if we're talking about genotypes. The problem is we know that selection acts at the, it has to work with the phenotypic characters, and that adds a lot of complication. So in these elementary models here, like kind of like what we'd say pedagogical or educational models, it has to start at the easiest just to make the, just to introduce the topic. And so Felsenstein's book, it's not, it's kind of accessible kind of in the early chapters where they have really simple models. Once they start dealing with phenotypic traits and diploids, and then other things like linkage and epistasis, it gets really nasty very quickly. So let me continue introducing some symbols here. So if we have a number W, we can call that symbol is absolute Darwinian fitness. And that just means basically how many children have survived, how many offspring individuals of that genotype have made and survived to adulthood. So this is, again, a highly idealized model. And Fisher's theorem would actually break down when we add even a little bit of reality to it, like variable levels of fitness across generations. It won't work anymore, or it won't work very well.
Yes, also, I wanted to say it cannot be exponential because there is a limitation on population size, and so it cannot grow exponential.
Yes, and in this case, they assume infinite population sizes, and you'll see that in Felsenstein's book. So a lot of these so you can already begin to see where I began to have find some of these questions, some of these issues a little bit disconcerting, because they're parts of population genetic literature that are based on highly idealized models. And then kind of the later generation of population genetics with Kimura and Crow, they began to use finite populations, but then the math got harder. So that's a good point. So these are dealing with infinite populations. And so when one is citing the literature, one has to kind of be cognizant what context the equation is being applied to, how idealized the situation is. And so when Felsenstein was referring to the one locus approximations, that Fisher and Wright's one locus equations turned out to be approximations, sometimes bad ones. This is probably one case, probably one of the approximations that may be bad. So that's a good point. But nonetheless, and I need to point this out, this was claimed to be biology's central theorem. And if it's based on approximations that may be bad ones, it probably shouldn't be biology's central theorem. It's not in practice, it hasn't been, but it's more of a myth that's been perpetuated. So you are correct. So just simply, I'm just gonna just fast forward here. So let's just take a simple example. Let's say we have a population that's constructed of several subpopulations. And we'll see this in Basener and Sanford's paper. They talk about subpopulations. So this is basically like if you have a population of one species. And again, let's consider the haploid, the haploid asexual model. And the other idealization is that all the parents have all their kids at the same time, because the math starts to get kind of nasty. So we have to add even more of this to make the math, particularly in the discrete case, work well. So let's say we have one genotype that results in the subpopulation having.
So am I right that you say some subpopulation have the same genotype?
Well, one way to look at it is, let's say we have a whole population of individuals, and one genotype results in the individuals having 4 offspring. And I had a little table here. Another genotype has 3 offspring each, and then another just 2.
Okay, so it's just a grouping by the same genotype, correct?
Right, right. So
okay,
every individual with that genotype will have exactly 4. Now, Felsenstein goes into some of the more he explores the math when that approximation is valid, because obviously that's an idealization. No genotype is going to have exactly the same integer number that survive to reproduce. So even in a bacterial population where there's binary fission, not every offspring will survive to reproduce. So again, this is an idealized model. What Dr. Felsenstein told me, he said, just kind of imagine the way to maybe model this is we have plants that have seeds, and then all the seeds are planted and they go off to be reproduced. That way you get them having their offspring at basically the same time. Again, these are all approximations, and he does. I was impressed that he pointed out when these approximations are reasonable, and then what adjustments have to be made when these approximations are no longer valid. So are you okay with the idea that absolute fitness, in my example, we can have it at 4 and at 3 and at 2? It just means the number of offspring per individual that survive to reproduce. So that means
yes.
So this is
fine. Also,
go on. I'm sorry.
Okay, sorry. I wanted to ask, does it mean that each individuum in subpopulation have the same traits, same genome? Or it's like they can have differences in genome, but they have the same reproductive rate? It is also the point here.
I didn't get the last part of what you said, but let me just say this. Assume that this is the only gene that's in consideration, and assume for the sake of argument they're identical otherwise in the genome, that they're just differing by this one gene. So we have different alleles. Again, this is, you could see how many simplifying assumptions we've had just to even get to this level of math where it's tractable.
Okay, so we assuming all subpopulation have the same gene and the same reproductive rate because of that gene. Okay.
Yeah, so just assume that they're identical except at that one gene location. At that gene locus, they have 3 different alleles. And I just call it allele 1, allele 2, allele 3 at that same gene. I'm going to point out that once, this is historically speaking, once they began to go to like 2 or 3, even 30 different genes, more than one locus. So gene is, we call it a locus, is meaning the gene is physically located somewhere. When they started to consider like two genes, which would mean 2 locations on the genome, they began to see that there began to be some complications. When they got up to 30, the math got really bad, and they started needing to do computers. But so it may be surprising that from a historical standpoint, that so much population genetic literature had to start out with this very simplistic model. And so in Basener and Sanford's paper, the reason the math got so, the equations were just so crazy looking, is it had to account for multiple loci, multiple genes. They didn't specify a number, they just probably used the idea of n. So you have multiple genes, like in the human genome, there'll be what, 20,000 that is the accepted figure for now. That could change, of course. And with each of those genes, there could be multiple alleles. So when there's a mutation, a new allele is created for that gene. And the terminology they use is that gene locus. if you can hang on just one moment, I may have to pause. Let me do this. I'm gonna pause the recording. I have to do one thing, Peter, hang on. So let me go back to sharing my screen. By the way, you're welcome to download my paper. I can, when we post this on YouTube, I probably will include a link to this paper, and
Yes,
then also
nice.
a link to Joe Felsenstein's free population genetics book. And if there are discrepancies between what I wrote and he wrote, you're more than welcome to comment on that. I would actually value the correction. So anyway, just then imagine, even though this is unrealistic, just for simplicity, just imagine that we have a creature that had a genome composed of only one locus, one gene, and that in the population there are only 3 alleles. So you could say red, white, and blue. I don't know. But the point is, in my example here, just for pure illustration, individuals carrying allele number 1 of that gene can reproduce at a rate of 4 children per individual with that allele. And then individuals with the number 2 allele for that gene can reproduce at 3 offspring per individual, and so on and so forth. So one could see, under an exponential growth rate, over time, the allele number 1 will dominate the population, independent of the initial frequencies. So let me just move on. I'm stumbling a little bit, but the idea is, if we have an initial, so you'll see here, and this is notation you'll see, I believe, in Basener and Sanford's paper, this PI, that is the population, the absolute population size. Now, Dr. Basener may use a slightly different convention, and we may have to work through that. So the PI is the population size for that allele at that gene locus. In this case, it's nice that we're only assuming 1 gene locus.
Okay, and E is subpopulation number.
Right,
Okay,
the size,
yeah.
the absolute size. And that's the convention that Joe Felsenstein uses. He may use slightly different notation. So I use the capital PI to represent the absolute population size. K is that generation. So generation 0 is, I designate that as the initial numbers in this population.
Mm-hmm.
Now, this may be a little bit funny, because it's like, well, I just said earlier, we're talking infinite population sizes. Let me amend that. It can get up to infinite population sizes. And then I'll show why it may or may not be relevant, because a lot of population genetics is not written in terms of absolute fitness or absolute population sizes. It's in terms of relative population sizes. They may use the word, yeah, go on.
Yes, I got it. I see that you divide it by variables, so you sort of normalize the population that make it not infinite.
Yes.
Okay, yeah.
So
yes,
that's exactly. So what we have here is we normalize a lot of things. So the absolute fitnesses, it gets normalized to a relative fitness. There are various, there's no convention as to what allele we're going to pick to be the reference point. It's kind of, in my example, I just picked the allele that was the most prolific, being 4. So then we can see then that the relative fitnesses are scaled to the most prolific one. So all I did was I took this number and divided each line by 4, and you get these relative fitnesses. And the same can be done essentially, and I'm glad you're math savvy with the population sizes. We can scale them to be relative population sizes. So I don't quite know the convention in Bill Basener's paper, whether the PIs were absolute or relative. In Dr. Basener's paper, I think he uses M instead of W. Like I'll use this WK and he'll use an M. So just to step back a bit, the most general form of Fisher's theorem doesn't use discrete generations. If we went to continuous time model, the math is considerably more difficult. So I just need to pause here. This is mostly for education that I'm choosing the discrete model. So if you go to
yes,
Fisher's,
but I find it okay with discrete because we calculate over discrete populations. So it's sort of fine for me.
okay, thank you. So I just wanted to mention that. So if you go and see the literature on this, it's like, well, it doesn't look exactly like this. There are versions of it that are discrete, but the most general form is continuous time, and so the results will look a little different. So let's see. We can now, so we have population sizes, and then we have relative population sizes, and then relative fitness. From that, we can just generate the mean fitness, and this follows from calculating the mean in just standard statistics. And it wouldn't hurt if I just, even also for my own benefit, if you'll permit me, see, okay, so just for the reader's benefit and then also mine, we often denote the mean, and this is from a Wikipedia article. So like, let's say they're using the symbol X to denote all these values. The mean is denoted by X with a bar over it. And it gives a method of calculating the mean. And you could see it here. There are variations on this. That's basically what this is, just different symbols. So people familiar with statistics, that should be pretty easy. Likewise, there's a definition of variance. And one can look up the Wikipedia article, and it wouldn't hurt. There's some subtleties.
So may I ask?
Yes, by all means.
Okay, so it's mean per entire population. No, here. Yes.
Can you state that again? I'm sorry, Peter.
So this is the mean value over entire population. So
mean value over the population of the fitnesses.
Yes, okay.
Right. And then there is this one. You can also calculate the variance from the mean. And just for the reader's benefit and also mine, my math training was not in statistics. It was for physics-based. It's just amazing all the different specialties in math. So I do fumble with this. There is a definition of variance. So I think, let me see, if I get this.
Yes, this is definition.
Yeah. So let me see if I have, let me see if I can get the wiki part again, just to, it's gonna also give for my peace of mind. One thing that someone has to go through is the symbols are different, and that just has to be worked through. So you could see here, the variance here looks very much like this. The symbols are different. So instead of WK, it's just referred to as mu here. And you could see this is, it's just a matter of being able to translate standard definitions and their symbols to our specific particular example. So use this one for the variance. So we had the mean and variance, and it's that simple. So this is just slugging through it, and then this will relate to Fisher's, to Basener and Sanford's paper. But The bottom line is this is Fisher's discrete version. This is not the continuous time. Dr. Felsenstein will say, well, it's not really Fisher's theorem. Others will say it is. And I'm not going to get there. This is educational enough to get the idea of what Basener and Sanford's paper mean. Okay, so if we define what I call delta, let me define this quantity here. Delta W with WK. And let me see, here it is. So we have the mean fitness in one generation, K, and then the mean fitness in the next generation, K plus 1. That's delta WK. That's how I define it. You may not find that in textbooks, but for the sake of the paper, this is how I defined it. If one reads some other textbook, they'll just have to make an adjustment, but I tried to simplify the terminology.
Okay, so it is relative fitness growing speed, I would say.
Yeah, it'll change over time with each generation. So this is just the change in one generation. Is that okay? Did I describe?
Yes.
Okay. So I specifically said this definition of delta WK, and I'm glad we can do it with symbols because without these symbols, it'd be confusing if they just went by an audio book. That's why I could never teach math through an audiobook. One needs to read symbols. So it may not be in agreement with other texts. I just did this to make the point a little clearer. And then this explains Fisher's theorem. The change in the mean fitness, you take, so this is basically what happens in the next generation. The change is the variance in the present generation of fitness divided by the mean fitness. And if we look at, let me just show the Wikipedia version of Fisher's theorem. And the reason this is problematic, Fisher never used formal math symbols. This is how he stated it, and everyone had to try to figure out what he meant. He said, the rate of increase in fitness of any organism at any time is equal to its genetic variance in fitness at that time. And then they say in more modern terminology, the rate of increase in the mean fitness of any organism at any time that is ascribable to natural selection acting through changes in gene frequency is exactly equal to its genetic variance in fitness at that time. So you could see how, and George Price in the 1970s pointed out, this was part of the problem. It was not stated rigorously in terms of math symbols. What you'll get at the Wikipedia version is the continuous time version. So in the continuous time version, this denominator here will approach either 1 or 0. What ends up happening is you end up just dropping the denominator. As we go from the discrete to continuous time, that denominator disappears.
I want to ask.
Yes.
It will be as differential of k if it is continuous.
Yes. So what'll happen is just in the continuous time version, it'll be the mean fitness equals the variance. And for any of our readers who are savvy, if I misstated that, please let me know. I'm only more familiar with the discrete version, and it looks like Basener and Sanford's is also the discrete version. So again, also from partly because of computational issues, it's really nice to have at least some discrete approximation. So just take it for what it's worth. This is just to give a little bit of the flavor of what Fisher's theorem actually stated. Now, one could see where the problem is if fitness actually varied across generations, even if we had some nice mathematical formula for describing how the fitness changed over generations, the theorem may not hold. So it works, suffice to say, it works really, really well when we have constant absolute fitness. And what Basener and Sanford did was they said, okay, what happens if we start adding new alleles, particularly ones that reduce fitness? Let's see what happens. And that's all the paper really explored. In my opinion, that was interesting, invaluable, but they actually did it at a time when a lot of population geneticists had already given up on it quietly, even though in the popular literature, like Richard Dawkins, he was advertising it as biology's central theorem, but professional population geneticists wouldn't say that. So we had kind of two cultures, the popular culture, which is going on an idea that wasn't accepted by the specialists. And so that's the situation. And that kind of, in the wake of Basener's and Sanford's paper, there was a debate how fundamental it really was, because all the professional population geneticists were saying that this paper's not very useful at this time because none of us use it. And then that came as a surprise to a lot of people, because we have Richard Dawkins and Ronald Fisher's Royal Society page uses the word biology's central theorem. Let me see. Let me just, Ronald Fisher, Royal Society. So at the Royal Society page, it'll actually, let me see. There it is. He was also a key figure in experimental design, providing researchers in biology and medicine with their most important research tools, as well as the modern version, of biology's central theorem. So I'm just pointing it out. We have a difference between the popular culture perception and the actual utility of the theorem. So how does this relate to Bill Basener and John Sanford's theorem? So keep in mind this, where you have the mean fitness, and then it's equal to some variance. So now I'm going to go to Basener and Sanford's paper and to try to help the audience with, see if I have it. Apologies. I'll need to see interview. And so now let's go to Bill Basener and John Sanford's paper to understand the meaning of it. And so now let's go to the bottom line. Now the early part of the paper referenced this from George Price. I'm sorry, George Price. This was nasty math, and I looked into it.
Okay, can you explain this, please?
Yeah, I don't think anyone explains it. It's not really part of the derivation in this paper. It's just more historical reference, because I don't believe Bill Basener actually used this. What he did is he appealed to later literature. And I'm not trying to brush that off. I don't. It's important historically, but he used a different starting point. So let me show the readers again this equation here. This looks nothing like what this is what actually is a little bit shocking, is when one sees this, it's like, that doesn't look anything like what we see in treatments of Fisher's theorem. I've hardly seen it. And what I mean by that is there was a paper by Lessard, and I think it's important that I go here, the population, Ewens and Lessard. So the more I'm going to try to remember to put all these papers here, links to it, and these are public domain to the best of my knowledge. You'll see that when they deal with Fisher's theorem, they don't use the symbols that Price uses. So when one sees all these huge number of summations, this is when we're starting to add more alleles and locus, multiple genes, multiple alleles. The math gets nasty really fast. And you add to that the diploid stuff, it gets even worse. So let me show you where they had the discrete version here. Okay. Let me increase this here. Again, the symbology. So do you see equation 13 here? Where it has this, the mean W, and then sigma squared is usually the variance. Right, standard deviation is the square root of variance. So sigma squared,
Okay, good.
sigma is standard deviation, so sigma squared is variance.
Yes,
so we have that
where is
sigma squared is variance.
Yes.
Okay, so in my
mean fitness, yes.
Yeah, this is where it gets a little bit hairy, is that you could see in my note, you could see the difference in my notation here versus this. Ewens and Lessard are the most respected people, so I'm not going to try to say that my notation is better. I used a different notation for the sake of readers not familiar with population genetics. So let me just put them side by side here. Oh, it's not, apologies. I don't know if there's any way I can separate out the paper. No, it's not gonna, is it gonna let me do that? Yes. Apologies, Peter, I'm just having a little bit of a technical problem here. So let me just try to put some of this side by side. Let me just shrink this a little bit more even. So you could see the way that I stated it here with the mean fitness. They use a partial derivative, and that gets into some interesting reasons why they use that. And they use sigma squared instead of variance, and then omega, and they don't use k. So it's assumed this is the discrete version. So that's one of the problems in reading through population genetic literature, is everyone's using different symbols. The reason I went through the trouble of emphasizing the dependence on k is it's not always clear. It's not always clear what's being described. K just, this is, it's more for non-population geneticists that I use this kind of notation here, but it will relate to Ewens and Lessard's paper. So going back to your question about that complex part that looked kind of nasty, I've not really seen it delved into in modern literature, except for Price's paper, where, so going back to Basener and Sanford, hang on, let's see. So this came from George Price's paper, his famous 1972 paper. That was actually not from Bill Basener. But then I don't think it ever got used in Bill Basener's paper from that point on. He went to a different formulation of some of the ideas, and it would be kind of along the lines of Ewens and Lessard's paper. But let's just get to the bottom line. Let me see if I could find the bottom line. We don't have to suffer through the proofs, but you could see here, you have the change M instead of W, he uses M, Dr. Basener, and then he has the variance in M. Now this extra term here is probably because of the added mutation. So Fisher's original model did not have any infusion of new mutations. So the difference that was added here is when we're infusing new mutations, the math changes. And you'll see in the paper, it said, strictly speaking, when we start to add new mutations, it's now modifying it modifies the original theorem. It's now, it really is a different theorem at this point. And I just wanted to point that out, that it's somewhere in the paper they say, well, this is now not exactly the original formulation of Fisher's theorem, because the original formulation didn't have mutations. So one can debate then what the effect of this is. So that's basically my best understanding. All this other stuff is now we're starting to add more gene loci. So it gets really nasty when you add more gene loci and then also adding new alleles at those loci over time. And that's why the math got so nasty here. Whereas kind of in the simple model like mine, not really mine, but the simple discrete model, the math is just, it looks more elegant and simpler because it's modeling a more um, it's modeling a more simpler situation. So you could see here, okay, so this explains it. This is a continuous time model, so you no longer see the variance being divided by anything. So like I said, when we go from the discrete to the continuous, the things in the denominator disappear. So I hope that's my best attempt. I welcome any viewers who may have had issues with what I said. Please somehow put it in the comment section of this video and with links or to an explanation. And I would be personally very grateful, but that is my best understanding. So there were other things in your email that I didn't get around to, but I think this is maybe a good stopping point. Do you have any questions, Peter?
Okay, so I would ask also what is BJ and FJ stands for here. That would be nice.
What is what?
BJ and FJ in this formula.
I don't know. I don't know. That's.
Oh, you don't know.
I do not know. I do not know. And I'm sorry, I don't. I've worked with Bill a little bit, and we had what he did, and I really should. I didn't acknowledge him in my paper here because I didn't want to get him in trouble in case. But he did. He said, yeah, he said that my description of the simple version is correct. He agreed with that. And so how it relates to when these other indices, I don't know. So I believe one could see that, oh, here it is. You could see that this is, again, this definition, the mean fitness.
Yes, it's mean fitness. Mm-hmm.
Yeah. So the PIs could either be relative or absolute. It may actually be equivalent. You could use either. That would be an interesting theorem. So I think it may be one of these that it won't matter because it's the proportions. If you, I think it'll all work out. If I'm wrong about that, then apologies in advance. So at least we have, you could see this M here, and then the change in this M bar over time. So this mean fitness, the change in mean fitness over time. So that's at least, I got at least that part of the symbol. So now, as you said, what are these BI and FJ? And I presume do you have the paper handy? If not, since we're talking about it, we might as well try to look. The birth rate of the if subpopulation and the death rate DI. Oh goodness! So that's some sort of the birth rate of the if population. So BI, and then I'm just going to have to refer the reader to this here, this paper. And FI, I don't see where FI is the fraction of the bursts that are in PI. Okay, so he has it here, and I'm not, if you'll forgive me, that's about the limit. I'm probably going to get myself in trouble if I go beyond the text. And certainly live on YouTube. I'm not going to venture to try to figure out the meaning of this, but it is detailed there. And that's about the extent of how I could be of service to you today. So I hope I've at least been able to be a little helpful in clarifying what the paper was about. So maybe just to back up a little bit, the math and the proof for the fundamental theorem of natural selection has been well established. And the original math assumed no added mutations. This theorem adds mutations, and then we can add deleterious mutations. I think this formulation is general enough to allow for beneficial mutations as well. So it's not just negative, not just deleterious mutations. So the reason this got into the journal Mathematical Biology was this amendment to the original theorem to allow mutations. So Dr. Sanford is not a mathematician. Dr. Basener is. He's an emeritus professor of some technology institute. He's now a professor in University of Virginia, which is near me. That's why I've had the privilege of meeting with him personally. And so that's about it. He took something, he took work by others, named most importantly Wilkie, to formulate some of this. And so that's basically what the theorem states. I think the only complaint, the two major complaints I have heard from critics, including Joe Felsenstein, was, well, first off, Fisher's theorem was never fundamental to begin with. So basically it's knocking down something that's already dead as far as population geneticists are concerned. The second thing is that, Fisher's theorem is already dead. The model did not deal with epistasis and linkage. And I believe recombination. And I pointed out even Felsenstein's colleague, even when you add all that in, independent of Fisher's theorem, there's a point when the population will decline in fitness anyway. So that was the other one. And those were the criticisms. I never heard that the math was actually wrong. It was criticizing the underlying assumptions, but then the argument is, well, if we do make it more realistic, it really just does strengthen the point. So that's all I had. I personally, by the way, I don't argue creationism by using Fisher's theorem. So Peter, did you have any closing thoughts? And we can have another meeting on this. You had many more questions in your email. And
okay, thanks. Yes, you have explained it a little bit. I will go further to understand these formulas properly. And I would actually have further questions about this Mendel's account program, right?
yes, even though I had been Dr. Sanford's research assistant for 6.5 years, and I'm still his research assistant, Mendel's accountant is not my specialty. He had quite a number of research assistants working for him in different specialties. Mine has been on the ENCODE project and studying protein and structural biology, and a little bit of bioinformatics. So I'm the only work I did on Mendel's accountant was there was one version that was running on the cloud, and I helped build the self-installation, the self-installation package so that people can install it on their computer. And I don't believe that version's even in use anymore. So I'm sorry I can't help you there.
I wanted to ask, is it possible so I take the Mendel's account model and program it for myself? Just
I think
version.
I think what I would encourage people to do is just to not even try to use Mendel's accountant the way it was implemented. Just build your own from taking Joe Felsenstein's population genetic book and trying to model the examples in there, and then try to add deleterious mutations. I will tell you, though, what was very interesting, since we're talking about Felsenstein's book. By the way, I would love to address your other questions in a future show. Would that be all right with you if you're interested? Because I thought you had good questions if you'd like to talk about that, because in our short segment, I don't think I could possibly cover all your other questions. Would you be interested in the future show?
Yes, I would like, I said, I would like that you explain how Mendel's account working.
Yeah,
So
and
is
I
would
can
be
tell you just
possible.
up front, I don't know. I'm really,
Okay.
really sorry. I know that there are a lot of creationists that try to argue in defense of it, and I'm just like, me personally, I would prefer to just argue from as much as possible from existing literature. And I will tell you that there are, that relates to the quotes about Ono and Muller, and maybe that would be a better talk. And again, I apologize in advance. I found it personally not productive to be trying to defend the case for creation based on Mendel's accountant alone. I found it to be more productive to appeal to known literature, like Ono, who coined the term junkDNA, and
Yes,
Muller.
but
I'm not trying to say that Mendel's accountant is bad, but since it's was written by creationists, this distrusted, so I'd rather appeal to mainstream sources. It's just
okay.
as simple as
But
that.
it's not the problem. I wouldn't just to recreate the Mendel's account for my own and look how it's working.
Yes.
So that
Okay.
was my question.
Can I
So
tell you, to the best of my knowledge, and it's a very sad story. The last version of Mendel's accountant was written by a software developer, but he died of cancer suddenly. And so he would have been the point man to be asking these questions, but he died. And so the software is not maintained. And Dr. Sanford has moved on to other research projects, such as Adam and Eve, the Adam and Eve question, because he collectively in the creationist community, we felt once the secular community, as far as human genomics is concerned, once the secular community started to say they think that the human genome is deteriorating, that was adequate. We no longer felt we had to prosecute that case because many many geneticists studying human heritable diseases, to a man, almost all of them are saying we're degenerating. So we never felt we had to make the case specifically for humans anymore, because
yes, but
yes,
the question is, what is the reason? What causes the deterioration?
yes, and that is Muller's limit, which I think, can I, if I can,
Yes.
we had that email that, let me see, I don't want to show that one. Yes, so in your email, sorry, I don't want to, apologies if something private got through. I'll edit it out in our thing if I see anything that violated your privacy. So don't worry about that. Just for the readers, for the viewers' benefit, I want to protect people's anonymity. I try to minimize any talk about any personal details. I feel that if we stick strictly on the questions that are technical, and then that's the thing that's important, and then more people will be probably more willing to interact with me live, and that helps the channel. So why is the human genome deteriorating? The creationist answer is, this was from my slide. one of the slides I presented, it said uh, if the overall deleterious mutation rate per generation becomes 1.0, that ends up being too much to bear. And that's where Ono coined the term junk DNA. And that would be a good topic. Now, if anyone Googles the word Muller's limit, they will not see it in professional literature. That's the term that I coined to describe this phrase here that I highlighted in green. That's all it is. So if people don't like me referring to it as Muller's limit, that's fine, just as long as we understand the number that it's referring to, meaning 1.0.
Okay, so I wanted to ask, how do you come to that number?
Yes, that would be the subject of the next segment, because my
okay.
voice is running out, and I'm not trying to cut you off. I think that's a great question, but I'm definitely running out of gas, and I have to attend to something else shortly.
Okay, it's fine, so.
Yes, so if there, by the way, in the next show that we put together, and by the way, thank you very much for being my co-host here and asking questions. If there are things left over from this discussion, any loose ends that are just really nagging, we can cover that. And I value very much your questions, and if there are things that I've said that are wrong, I value getting that corrected, because shows like this are really intended to be educational, and it'd bother my conscience if I taught something wrong, in the sense that of the correctness mathematically in terms of the terminology. Even though we are dealing with models that we know are just approximations, that's a given. But within that model, I would like to state things accurately as far as the inferences that are made within that model. So yes, granted, the underlying premises of the model, such as like the discrete generation and no change in fitness, that's a given that we know that those are only approximations. There may not be very many real world cases where it's applicable, and that's totally fine. So
yes, it's fine. So the main point now is to explain all the stuff properly, and you did great. Thanks for that.
yes, so that'll do it for today, and thank you for joining us. And
Okay, thank you too.
Yes, and I'd like to thank all of our viewers that have stayed with us to this point. So I'm going to shut off the recording, and I'll meet you briefly backstage, Peter, just to say thank you. So
Okay.
have a good day, everyone.